all. In today's session we are going to discuss about the Yagi Uda antennas. Now as we know that as we increase the number of elements the directivity increases. Okay? So here we have talked about the arrays also. So when we talk about the arrays, so array is nothing but where you are having more than two elements, or you can say more than one element, but here all elements of the array are active because you are giving feed to each and every element. Now here what will happen, now you need to give the feed to each and every element. What will happen if you need to simplify the feed network? You can give some of the input, or you can give the input or feed to some of the elements, okay, and other elements can be kept as it is. So the elements which are not fed directly will be called as the parasite element, while those are fed by the feed network are called as the active elements. So active elements, the elements to which the feed is given by feed network, and the parasite elements are the elements that are not fed directly. So here we'll talk about the Yagi Uda antenna. Now it is nothing but the array, or you are having number of elements more than one. So how I'm going to define the Yagi Uda antenna? So Yagi Uda antenna is an array consisting of a driven element and one or more parasitic elements. They are arranged collinearly and close together. The basic unit of Yagi Uda antenna consists of three elements. Now to understand the operating principle of three element Yagi Uda antenna, let us start with only two elements first. So here we can see one is the driven element and other one is nothing but the parasite element. So initially we have considered only these elements. So consider here if I talk about this one, this is nothing but the given feed to that particular element will be called as a driven element. So here I am assuming right now this particular driven element is of a length lambda by 2. Okay, and the spacing here if you see is between these two driven element and this as not fed directly will be called as a parasitic element. The distance will be 0.04 lambda. Now when the driven this active element or a driven element is excited by the feed system, it radiates a field which will be tangential to the wire. So this field will be incident on the parasite element. This is a parasite element. Since the spacing between two is very small, almost all field radiated will be incident. So thus the incident field, or you can say the incident and the radiated fields are equal in amplitude. So here you can say that E incident will be equal to E driven. Now here as we can see, the incident field generates a current in this particular parasite element. So the current excited will cause a field radiated by the parasite. So this field also tangential to the parasitic element and equal in amplitude and opposite in phase to the incident field. So this is because the total field tangential to the parasite element is the sum of incident field and field radiated by it. So according to the boundary condition, the total electric field tangential to a good conductor is 0. That is, you can say here E incident plus E parasite is equal to 0. Now E parasite will be equal to minus E incident, which is equal to minus E driver. Now here, thus the array shown in this particular figure, you can say it's consisting two closely spaced equal amplitude, you can say, but the opposite phase elements from the array theory. So the radiation pattern must be dual end fire pattern. Now let us increase the length of parasitic element. The length of the parasitic element is made 5% longer. If we made this particular parasitic element 5% longer, then we can say lambda by 2 dipole. So here we can see here driven element is of 0.5 lambda, and I have make a 0.55 lambda as a parasitic element, so that it is inductive. Now using a numerical method, if the analysis is made, the H-plane pattern will be like this. Okay? The pattern is not a dual end. Now previously we have seen the pattern was dual end fire, but the pattern is not a dual end fire pattern. It consists of a single main beam occurring in the end fire direction from the parasite to the driver along with the line of the array, as you can see here. Now it seems like the parasitic element, which is longer than the driven element, is reflecting the beam on the left side in the right direction. So reflections goes here, which results in a single beam in the right direction. Now that is why the parasitic element longer than the driven element. Now here, as we have concluded, our parasitic element is nothing but the longer than the driven element. You can say here the parasitic element longer than driven element is called as a reflector. Now let the parasite is 5% shorter than a driven element, but now we'll place that particular parasite element on the other side. So as we have already gone through the previous pattern, we can say this parasitic element which we are placing right now on the other side, this parasitic element will be called as the director. So the parasitic element, the parasitic element shorter than driven element is called as director. So here let us see what kind of pattern we'll observe with this. Now this is nothing but your driven element. So I have drawn this driven element over here. These are nothing but the feed points, and this is nothing but the shorter element which I have placed next to that one. So I can say this is nothing but the Z direction. This is nothing but the X direction. As usual, we are having 0.04 lambda. Okay? So we can say here this is nothing but the driven element, which is, we know that the length is 0.5 lambda, and this will be nothing but the parasite element, which will be having the length of 0.45 lambda, as we have made the length, we can say, shorter than this particular driven element. And now let us see the what kind of the radiation pattern will get because of this particular thing. So here I have a driver, okay, and here I have a director. Okay, so here whenever you observe the radiation pattern because of this kind of things, the radiation pattern will be like this. So this will be the Y, this will be the Z. So you can see because of this particular driver you will get this kind of the back lobe here, otherwise you can say the back radiations, you can say. Okay, and you'll have this kind of the pattern. As your director will again add the radiations in your, you can say, driven element. So this kind of the pattern. So you can say this is nothing but the beam enhanced in a right direction. Okay, so here driver and the director arrangement, this is nothing but the H, you can say, plane pattern using the numerical method, where you have got this kind of the radiations. Okay, now 3 element Yagi Uda. This is all about what we can have when we are adding the directors and the reflectors in the driven element. Now let us talk about the 3-element Yagi Uda antenna. So 3-element Yagi Uda. So here in this 3-element Yagi Uda, I'll have a 3 elements, as we have already discussed about 3 elements. One is the reflector, other one is nothing but the driven element, and third one is nothing but the, we can say, your I can say director. And we can say that the radiation pattern which we have observed previously, and we have seen the separations between the elements equal to 0.04 lambda. So here let us talk about this 3-element Yagi Uda antenna. So the you will have this kind of structure in between. So this will be called as the, I can say, ठीक है, and this will be your driven element, this will be your reflector, and this will be nothing but the, I can say, directors. ठीक है, this will be the driver and this will be the reflector. Now let us talk about combined radiation pattern because of this particular 3 elements. So I can say this will be the Y, I can say this direction will be the Z direction. So as we know that because of this particular you'll get 8 pattern, okay, but because of the reflector, reflections will get added. So I can say this will be your driven element, this will be the director element, and this will be the reflector element. So what kind of pattern you will get here? H pattern. So this is nothing but the pattern where you are having this kind of the loop in the forward directions, as the reflections are, as you can say, the radiations are going to add in this one, and this is nothing but the backward radiations. So this is nothing but the how you're going to get. Now this is the H plane pattern. So if I talk about the E plane pattern, this is H plane pattern. So if I talk about the H plane pattern, I can say, sorry, H plane pattern I have already done. E plane pattern for this particular will be like this. So I can say this is the Z direction. So this will be the, you can say, loop in the opposite direction, and this will be the loop in the forward direction. Okay, so I can say this is the E plane pattern. Okay, now this is nothing but the how we can observe here. So you have this kind of things, the distance decides the magnitude and the length decides the phase of the current induced in it. Thus by changing the separation and the length of the element, it is possible to have a relatively unidirectional pattern if you are interested in doing this. So it will have a small back lobe which can reduced very easily here. Okay, thus the front to back lobe ratio of antenna is improved simply by decreasing the distance between the elements. So however, this has the adverse effect of lowering the input impedance of the array. So that's why you can find out the midway that how you can go for that particular things. Okay, now for 3-element Yagi Uda, following points must be remembered. So if you are using a 3-element Yagi Uda antenna, so you need to remember following points. You can say the maximum directivity. Here the maximum directivity obtained is nothing but the 9 dB. Maximum is about the optimum spacing for maximum directivity. So spacing between reflector and driven element, or between director and driven element, lies between 0.15 lambda to 0.25 lambda. So this is the second point to remember when you are going for the Yagi Uda. So typically the reflector length is 5% more than the resonant length of the driver and your director length. So you can say director length is 5% more and your reflector length, this is reflector length is 5% more than your driven element, and you can say the director length is 5% less than driven element. ठीक है. So the resonant length of the driver is typically about 0.47 lambda to 0.48 lambda. So as we were talking about the resonant length, so this should be the 5% more or 5% less than the driven element length at resonance. So now let us talk about the resonance length also. So here you can say the resonance length of driver element, or you can say driver, is typically about 0.47 lambda to 0.48 lambda. Now this depending on the radius of the wire used for the dipole. So you can say this depends on R of wire used for dipole. So this is all about the 3 element Yagi Uda antenna. Now let us we can say how we can improve the basic Yagi Uda. This is the basic Yagi Uda antenna which we have seen till now. So how you can improve the basic Yagi Uda antenna? So improvement in basic Yagi Uda antenna. Now we are having a directivity of 9 dB with the basic Yagi Uda antenna. Now you can increase the number of elements to increase the directivity. So only one reflector need to be used. So here reflector 1, one director. Here whatever directors you are using, increase the number of directors. So only one reflector needs to be used, as the addition of second or third reflector adds practically nothing to the directivity. So the directivity is improved considerably by adding more directors. So it increases from 9 dB to, you can say, 15 dB. So if you are using 3 element Yagi Uda, the directivity D max will be 9 dB. You can achieve, or you can increase it to 15 dB for 5 elements. Okay. So here you can have one driven element, one reflector, and you can say 3 directors. So how many number of, you can say, the directors can be increased? The number of directors can be increased up to 13, and after this there is no much improvement in directivity. That's why there is no need to increase, or there is no use of increasing the elements more than 13. Okay. The fourth one is, or you can say the next point is that the length of the director goes on decreasing as it goes away from the driven antenna. So the whole structure tapers in the direction of the propagation. So as director increases, you can say your length decreases. Okay. Next point says that all the elements are electrically fastened to the conducting or grounded. Okay. So you can say all elements are electrically fastened to the conducting, grounded central support rod. Okay. And the next point is nothing but the radiation pattern consists of one lobe, as we have seen, and lying in the forward direction along the axis of the array, with the several very minor lobes in other direction. So you will have here one major lobe and several minor lobes. Next point is polarization is in the direction of filament axis. So you will have a polarization in the direction of element axis. ठीक है. So if you see the 5 element Yagi Uda antenna, this will be the reflector. You can say this will be the driven element. You will have this will be the directors. 3 directors will be there. So I can say if I want to write here, and this will be the feed point to this one. I can say this one will be the reflector. This is feed point. This is director 1. This will be driven element. This will be director 1, director 2 and director 3. So I can say this element will be called, or this antenna will be called 5 element Yagi. So this is all about the 5 element Yagi Uda antenna. Okay. Now if I talk about the radiation pattern of such antenna, I'll get the radiation pattern here like this. So this will be like this. I'll have one major lobe in the direction of this particular rector. So I'll have a major lobe and I'll have a several minor lobes here like this. Okay. So I can say this is the radiation pattern with the 5 element Yagi. Okay. Now use a folded dipole in the Yagi Uda antenna. Now till now we have seen all the things were not folded. So here if you fold here the antenna, I can say Yagi Uda with the folded dipole. So I can write here, or I can draw this particular folded dipole. So I'll have this reflector. I'll have my driven element like this, which one is nothing but the folded one. Okay. And then I'll have 1, 2, 3 and I can say 4 directors, and I'll have this kind of the structure in between. Okay. So I can say this is my Yagi Uda antenna with the folded. So I'll say this is the reflector. This is, you can say, dipole, which is nothing but the folded dipole. Director 1, director 2, director 3 and director 4. And this in between whatever I am using is nothing but the supporting beam. Okay. And these are nothing but the feeds to this particular, if I am putting feeds over here, so this is nothing but the feed to this particular antenna. Now you can see here you are having a one driven element, one reflector. What will happen if you are using the folded dipole antenna here? So here Yagi Uda antenna is widely used for the television kind of things, applications. So here we know that Yagi Uda antenna, which we have seen, uses a lambda by 2 dipole as a driven element. Typically we know that Z in is equal to, for this lambda by 2 antenna, Z in is equal to 73 plus J0 ohm. Okay, near about. But if I talk about this folded dipole, it is having 4 times this, I can say, Z of this particular dipole antenna. So it comes to 92 ohm, which I can use for the television application. So impedance matching will happen over here, as I know that the impedance of my this antenna or this lead wire which I am using for the television, twin lead wire, is 300 ohm, which is nothing but the close to the 292 ohm. So this is used for the impedance matching, or you are having the impedance matching over here. So the maximum power will be delivered to such kind of the folded dipole antennas. Okay. So here you no need to use any balancing and unbalancing unit for this particular thing. Now let us talk about the applications of the antennas. So I can say application of this antenna will be, the first application, you're using it in HF, VHF and UHF range. You are using it in the TV antenna. Your major application is the TV antenna. Okay. Third, highly directive, it is used for the point to point communication. Okay. And the last application is nothing but these are also used for the base station. So base station on mobile communication systems where the working areas is strung out along a lines such as railroads, highways or pipelines. So this is all about the Yagi Uda antenna. In the next session we will talk about the design of 6 element Yagi Uda antenna.